here. Today I'm going to be telling you about some recent progress in something called the double copy, which has a long lineage in not just the theory of scattering amplitudes, which is what I'm thinking about currently, but also in quantum field theory and string theory previously. This is based on work with these folks here, James Mangan, Julio Palma Martinez, Alex Shivaramakrishnan, and Naba Shah. What's the big picture? So I'm going to start with just kind of a quick overview briefly of kind of why anyone might be interested in scattering. At least in my view, it's a very powerful diagnostic for identifying structure in QFT. The kind of usual story is that the way we typically compute in quantum field theory, which is with Feynman diagrams, has many advantages, but one grave disadvantage is that it's extremely complicated just technically to compute. It has a lot of built-in redundancy, especially if we talk about gauge theories or theories with general covariance. But if we instead just kind of stare at the scattering amplitudes like intrinsically in terms of their correct natural variables, their physical gauge invariant quantities, then we can find structure. So there's a long list of various structures, many more than I could put here, and which would include many other talks. But let me just mention a couple before diving into one of them, which will be the main subject of this talk. One classic example is dual conformal symmetry. So famously, if you take an on-shell scattering amplitude, which depends on momenta, P1, P2, P3, all the way to Pn, and you think of them as arrows pointing between positions in some dual space. So you imagine some set of x1, x2, x3, where the difference x1 minus x2 is P1, and x2 minus x3 is P2, and so on. You imagine a closed n-gon defining the space. There's actually conformal symmetry in that dual space that's preserved by these gauge theory amplitudes. And that's kind of a surprise, but a very interesting type of structure that you can see by just studying the amplitudes. Another recent development, or maybe not so recent, but one you've possibly heard of, is the so-called amplituhedron or associahedron, where we can think of scattering amplitudes as volumes, like literal volumes of certain objects in some auxiliary space. That is to say, there's some abstract notion of a volume. If we cut it up one way, we get Feynman diagrams. If we cut it up another way, we get another representation. And those all kind of more invariantly describe these on-shell scattering amplitudes. That's something which has gotten a lot of attention and also some recent progress in the last year. Another place where there's been a lot of fruitful progress is the idea that amplitudes could be correlation functions. So this actually was recently funded by the Simons Foundation for the celestial holography story, where very early on people realized that gauge theory amplitudes had the structure of correlation functions. In particular, the scattering amplitudes in self-dual Yang-Mills or the MHV sector looked a lot like two-dimensional correlation functions, and this kind of is the first, just by looking at the functions themselves, kind of mathematical insight that has led to things that are connected to the celestial holography and this infrared triangle of Andy Strominger and so on. Last but not least is the picture of gauge square root equals gravity, which is the very broadly the statement that there is a mechanistic weak mapping between gauge theory on-shell scattering amplitudes and gravitational scattering amplitudes. Okay, this is something which, of course, in its first versions appeared in open string, closed string duality, so-called KLT formalism. And the KLT mapping, what you learn is a relationship, a very direct relationship between open string and closed string amplitudes. When you take the field theory limit, it gives you field theory expressions for graviton and gauge amplitudes. But this kind of story has grown and extended to kind of a broader spectrum of ideas, which I want to tell you about in my talk today. So that's what I'm going to focus on today. In particular, I'm going to talk about a more kind of modern version of this double copy, which is definitely, of course, linked to the original KLT of string theory, but is more general, has been more broadly applied, and I'll argue actually goes, well, at least is kind of a broader field theory fact. Okay, and here's what it basically says in words, and then I'll go into equations shortly. So this BCJ duality says the following. It says that first, color and kinematics are dual. Okay, so that is to say the structure of the kinematic dependence in scattering amplitudes and the color dependence, that is to say the structure constants, have a hidden duality that maps the two of them. Okay, It's essentially some kind of isomorphism between the color and the kinematics of gauge amplitudes. So that's the first statement. And the second statement is that if you like grapple with that implication deeply, it tells you that you should be able to freely exchange color for kinematics because they are dual. Okay? And in doing so, you can generate the amplitudes of new theories from other theories. So there's relations amongst theories by applying this mapping, and you can just use this to compute things that have never been computed before. It's an extremely efficient way to compute. The idea here is to use the full force of 30 years of work computing gauge theory amplitudes, QCD amplitudes, and use that to get something out of gravity. Okay, so there's kind of a just raw practical tool, which I'll discuss a bit of, but also some underlying field theory structure, which is what I want to talk about. And so the very simplest version of this picture, which
Cliff, could I ask?
Oh, yes.
Yeah. Is this duality sort of an observation, or is it something that for which the reason is understood?
Very good question. I would say, in my mind, it is an observation in the sense of a mathematically true fact for on-shelf flat space scattering amplitudes. But the underlying reasoning, as I'll argue in the next couple slides, I think is completely mysterious, except in some cases. So in my mind, at least from the field theory perspective, it does not have a clean explanation. But I will give some explanations. Okay, so yeah, I'm precisely litigating that question here.
Okay,
but I would take it as a completely true, understood fact at this level for on-shell amplitudes. But as I'll mention, if you wanted to translate it even ever so slightly outside of the context of on-shell scattering amplitudes, there is mass confusion, which I'll get to in a second. Yeah. Cool. If you can just bear with me, you'll see what I mean.
Yeah,
but for others, let me just describe what it actually is. So the kind of famously the simplest version of this structure, you can see it's 3 particles. Okay, for 3 particle on-shell scattering amplitudes for gluons and gravity. Here's what they are, written in 4 dimensions in so-called spinor helicity formalism. Although I want to note that nothing about what I'll say depends on dimensions. So everything I say in this whole talk, sometimes I'll restrict to 40 because it's easy to show, but it's a general d-dimensional statement. Okay, but here's a statement. If you look at the 3-particle Yang-Mills amplitude, it has kinematics and color. The color is FABC. The kinematics is those angle and square brackets, which are just spinor helicity variables. So of course you can see immediately that if you take the gluon amplitudes and you take the FABCs and you just throw them away, take color, just chuck it, and you take the kinematics and just square them. That is to say, replace the color with another copy of the kinematic factor, you get the right column here, which is the graviton amplitudes. Okay, so it is simply just a mathematical relation at this point. If you think about things very deeply in terms of off-shell Lagrangians, like the Einstein-Hilbert action expanded in perturbation theory about a graviton fluctuation, this would seem extremely puzzling. Like the Feynman rules don't look similar in the way we usually write things. Of course, if you know a bit more, you know that Lorentz invariance actually uniquely fixes these objects. So it's not surprising that there's a double copy here. But the more surprising feature is that at higher point, 4-point, 5-point, and end point, and so on, this is a more general and true statement. Okay, so let me take the case of 4-point, which is where something first non-trivial happens. This here is a gauge theory amplitude, so just like gluon amplitude at tree level. Okay. Now, if you compute this, of course, there's the usual S channel, T channel, and U channel, and then quartic diagrams. And you can always write it just trivially in some form that you see here. So what is here? So we have color factors, CS, CT, and CU. So these are just the usual color structures, which are products of Fs, the structure constants. ST and U are just Mandelstams. And then NS, NT, and NU are kinematic functions, kinematic numerators. That's why they're called N, little n. And these depend on polarizations and momenta and so on. Okay. They could also depend on spinors if you choose to compute that way. It doesn't matter. Choose any way you like to compute. NS, NT, and NU contain the kinematics, and the CS, CT, and CU is color. Okay. Now, again, just to make sure we're on the same page, you might worry about the quartic coupling. There's some quartic contact vertex. You might say, oh, wait, where is that? These all have poles in ST and U. Where's the quartic? But just keep in mind that, of course, you can take a quartic and write it as S over S, okay? And then absorb that S in the upstairs into NS, for instance. So this structure contains any contact terms. Trivially, you just put it into one of the terms. It doesn't even matter the way you put it in. Choose any way you like, okay? The point is you can always just put the amplitude in this form. Now, here's the non-trivial statement. Well, so let me start first with the trivial statement. The trivial statement is that, of course, CS plus C2 plus CU equals 0. That's just the Jacobi identity mandated by the usual features of the Lie algebra for color. What is much less obviously clear why it should be true is that the same happens for the numerator. So ns plus nt plus nu is also 0 on shell. Okay, so the statement is if you compute it off shell, some 4-point gluon correlator, which isn't very physically meaningful, this wouldn't be true, okay? It would not sum to 0. But if you restrict to physical on-shell kinematics, which preserves momentum conservation, on-shell conditions, you find that ns plus nt plus nu equals 0. Okay. In fact, it does that no matter which way you compute this amplitude. It's just true. Okay. Now, and this is a statement about 4-point. Now, here's now what the leap is. Okay. So you see these two equations. One is about, products and traces of matrices. The other is about momentum polarizations. And you say, wait, they look exactly the same. So let me just commit to that mapping. Okay. Let me conjecture a duality that links them explicitly. Okay. That's a leap. Okay. It suggests that they're interchangeable in some sense because they satisfy the same algebraic identities. So let's replace one with the other. Okay. So what can you do? You can take the 4-point gluon amplitude, which I just wrote, and take the C's and replace them with the N's. Okay. This is called the double copy because it kind of squares the N's, squares the numerators, and throws out the color. Now, what's the magic here? Okay. The magic here is that you don't just get some random function. You get a function that has no color because you threw out the color. Okay. But you doubled the kinematics. You doubled the amount of momenta floating around. And it turns out that the object you get is precisely the 4-point graviton scattering amplitude. Okay, computing this 4-point graviton amplitude is super complicated if you use the standard methods. If you use just, again, I said Einstein-Hilbert, usual Feynman, DeWitt Feynman rules. It's like 100 kilobytes just to write that 4-point function. But this just is a shortcut to getting it. Okay. And it's correct. Now, again, why is this surprising? You can't just take numerators in a gauge theory and square it. It doesn't seem clear that you should be able to just square things and even get a gauge invariant object, right? The Ward identities are an intricate relation connecting different terms of different topologies. You shouldn't just be able to do this magic trick, but nevertheless, you get a gauge invariant correct answer, which is the 4-point graviton amplitude. And again, just to be very explicit here, yeah, yes, question?
Previously, before the double copy, NS, NT, and NU were functions of polarization vectors, right? And then when you square, a priori, the polarization vectors sitting in those factors are different, right? Which would be the ones that are appearing here in the graviton polarizations.
Yes, that's right. So there's actually, let me exactly jump on that. So I was actually just about to describe that. So inside, can you see my mouse, by the way? Can you see my cursor?
Yes, yes.
Yeah, okay, cool. So there's some NS here, right? And this NS depends on E mu, right? It's multilinear in E1, E2, E3, E4, because those are the polarizations. And that's just what the Yang-Mills amplitude is. When I square NS, this object becomes, if you like, a bilinear in E1, a bilinear in E2, bilinear in E3, and bilinear in E4, because there's two of them. The idea is that you interpret E1, E1, that outer product of vectors, as the polarization tensor for the spin-2 graviton in this theory. Okay, so you have a symmetric tensor. You can think of this as building the basis of cross and plus polarizations for the graviton. Now, of course, I didn't say it here, okay, but let me just say it in words. You could choose different polarizations for NS and N for the two copies. You could do an NS that's a function of E, and then an NS that's the function of E tilde, okay, which is formally another polarization. In which case, the polarization you get here would be E tilde, which would be a general D by D matrix. And that actually contains the graviton, the two form, and the dilaton, okay? Not coincidentally, the zero modes of the closed string, okay? Which is kind of more nicely how KLT works. But if you want other things, you can double copy in these richer ways where it's not a perfect square. Okay, so in other words, here I've taken double copy, I've taken NS and literally squared NS to two copies of itself. But you can take asymmetric copies where you take an NS from one theory, an NS from a different theory, and take their product. And then you also get new theories, which I'll tell you about in a second. Does that answer your question?
Yes, yes.
Sure. Okay, cool.
So far the statement is though is for Yang-Mills and Einstein gravity, right? Those are the theories.
That's right. That's right. Or you can take Yang-Mills with E and Yang-Mills with E tilde, double copy them, and you get Einstein gravity plus dilaton plus two form. Yes. But that's all
actions for some canonical actions for these.
Exactly. Yeah.
Yeah.
But it goes beyond that, as I'll say in a second. But let me just slow down a bit and just tell you what is known, what's true, what's conjectured, what's applied. So this double copy structure is a proven fact at tree level. So any endpoint graviton amplitude can be built from an endpoint gluon amplitude in this mechanistic way. Okay, so it's true for 27 gluon scattering squared gives 27 graviton scattering. That's just a fact. That was true, proven with BCFW and all these other types of approaches, factorization and so on. It's been recycled into loops using generalized unitarity, and that's almost tautological because generalized unitarity takes trees as input. So generalized unitarity is like the optical theorem, to the max, where you take loop integrands and you constrain them only so that on their cuts they are exactly the same as the tree amplitudes. So in some sense, they inherit those structures. This has been applied to great effect by Zvi and others in the study of finiteness of supergravities, studying supergravity amplitudes at very high loop order. And much more recently, we and others have applied them to LIGO. Okay, so that's for a whole nother talk, but let me just say it in words. As I've said, there's a shortcut, there's a cheat code for computing in gravity, which is to just not compute in gravity, compute in gauge theory and square it. There is an experimental program that really cares about gravitational observables, which is LIGO, Gravitational Wave Observatory. Of course, they don't care about gravitons. They don't care about scattering. So naively, it was very much aspirational, maybe 5 years ago, that you could apply any of this. But let me just say in 2 sentences what we did and what is now kind of a cottage industry in amplitudes. You can use these methods to build the scattering amplitudes for massive black holes in Einstein's general relativity. Okay, so this is a perturbative coupling, so we're always far from the merger event, but you can just think of them in the early in spiral, which is precisely what most post-Newtonian or perturbative calculations have been designed for 100 years, and LIGO uses those to great effect. The idea being the early in spiral, there's a weak coupling expansion, okay? And what we do is we compute black hole scattering, literally the scattering amplitudes for black holes order by order in G Newton. Then we use standard EFT methods to map that to a Hamiltonian. Okay, because you can map the scattering angle to a Hamiltonian. It's the inverse problem. And then from the Hamiltonian, you can get binding energies, orbits, and everything else that's actually relevant to the experiment. So as amusingly, the kind of state-of-the-art calculations in what's called post-Minkowski expansion, which is just order by order in G Newton. That's what that means. The state-of-the-art calculations are now done in amplitudes. They are done by amplitudes people. Which is already some progress. So that's a whole story I could talk about, but let me kind of fold it aside. That's not the topic of this. Let me move on to just the more formal points, which is double copy is more broad than just gauge theory and gravity. Okay, it's weirdly ubiquitous amongst nice theories, so this may be too small for you to see, but this is a table of a multiplication table of theories that you'll find in Zvi's review on the double copy. It of course has the usual, supergravities and super Yang-Mills theories with like n equals 4, 2, 1, and so on. But it also has other theories like the nonlinear sigma model, the theory of pions in the chiral element. It has Higgs supergravities. It has conformal supergravities. It has derivatively coupled theories. It has like a whole mess. Einstein-Maxwell has a whole mess of things that all square into each other. Okay, so if you have a theory that you like, Chern-Simon's theory. If you have a theory you like and has a name and one coupling, it's like decent chance it's on one side of this squaring relation. Okay, and I'm saying this to just emphasize that it transcends gauge theory and gravity. I just mentioned the case of gluons and gravitons, where you take gluon amplitudes, you throw away their color, and you kind of double their kinematics. But you can do the same thing for pions, okay? Let me tell you what I mean, and I'm going to really unpack this a lot, and I'm going to really go into this a lot in this talk. But here's the idea. I say by pions, I mean scalars in a chiral Lagrangian for G mod H symmetry breaking, okay? And those, of course, don't have color. So you're like, what do you mean color kinematics? Well, they don't have color, but they have a different internal symmetry, which is flavor, okay? So there's a flavor symmetry. Again, I'm in the chiral limit, so this flavor symmetry is something that's exact that I can organize my amplitudes in. I can color strip them just like I can flavor strip them just like I can color strip gluon amplitudes. And I can throw out the flavor structures and square the kinematics. Now, here's the remarkable statement. if you do exactly the same rules as I just mentioned for gluons, like literally with no difference, exactly the same, organize it in terms of those S, T, and U, do the square, you get amplitudes in a theory called the Galilean, or special version of it, which is relativistic. There's no non-relativistic anything. It's a theory of a scalar that has an extended shift symmetry. It showed up in hypothetical models of cosmology, and it's famously the longitudinal mode of a massive graviton. It showed up in HepTH for other reasons, but it just pops out. Okay, it's a square of pions. We don't know why, but I will tell you why. But it's confusing why you would expect that. Famously, the Galilean is also strange because it's inconsistent with ultraviolet UV completion because it violates these positivity dispersion relations as these kind of weird acausal features. So there's no statement that something has to square to a healthy theory, but it just gives you the full endpoint S matrix for the Galilean. Okay, that's just a true other proven fact. You can do even nuttier things. You can take gluons and pions and combine them. Okay. And I want to emphasize here, I'm not talking about gluons and pions as like related through some strong coupling phase transition. That's not what I'm saying. I'm saying take a weakly coupled gluon amplitude, take its color and just throw it away. Take a weakly coupled pion amplitude or NLSM amplitude and throw it flavor away, and then take their numerators, their kinematics, and take their product. You get the amplitudes in Born-Infeld theory. Okay, so this is like part of the general feature of these multiplication tables. And again, this is the same rules. KLT, if you like, also works for all these. Okay, in the field theory limit, those same expressions work. Okay, now okay, let's go through some natural things you might anticipate. Like surely the double copy must be the tetrad formalism or the use of the spin connection in gravity, right? We often are think of gravity as a gauge theory of the Lorentz group of SL2C or SO3, but it just turns out that's not what's happening here. Okay, you would have thought it'd be natural, but it's not what's happening. How can you determine this? It's easy. Just take a gluon amplitude and then replace the color with SO3, okay, you just literally just don't get the graviton amplitude. You just get a regular gauge amplitude for SO3, So it's just not what the mechanistic procedure is. You could try other things like tetradic Palatini or like Plebanski or self-dual Plebanski. There's all these different variations. And as far as I can tell, none of them give this formalism. And the reason is simple at a technical level. It's because even though we say gravity is a gauge theory, we don't literally mean that the Yang-Mills field equations for gauge group SO3, are Einstein's equations. In fact, they're not. The Yang-Mills field equations are not Einstein's equations, just with the gauge group SO3, Okay, so that's the important difference between them. Another important difference is that there's a tetrad in addition to spin connection. But unfortunately, it's just not obviously this. Although maybe there's some more exotic version of gravity, like non-metric compatible torsionful that could do it. That's something I'm thinking about, but it's not in an obvious way that explains a double copy. And that also wouldn't explain the pions or the gluons and pions giving Born-Infeld there. Now, is it open string, closed string gravity? I mean, so in principle, maybe this is just the miracles of strings. You have to put into string theory and then take the alpha prime goes to zero limit. Now, of course, there's something funny about that being true here because the Galilean doesn't have a UV completion. Okay, so like it's inconsistent with ultraviolet completion. So that seems a little confusing if it's embedded in a string. But let me just say, like, okay, as a matter of principle, I personally think that if something's true in QFT, that's true for many quantum field theories, it should have a quantum field theory explanation. It would be weird to me if you have to embed it inside some string compactification and then like take alpha prime goes to zero and then determine it to be true. And that was the only way. Okay, so in other words, I'm interested in whether there is a QFT explanation for this fact, and I will tell you one in my talk today. Okay, so harkening back, the double copy is a proven fact about on-shelf flat space tree level scattering amplitudes. That's a lot of caveats. That's a lot of specific, sub cases. If you ask someone at an amplitudes conference, like, why is double copy true? They'll tell you and list off like 5 different proofs, which are just mathematically true proofs. They're totally fine. They work at endpoint. But their issue is that any epsilonic perturbation away from any of these assumptions destroys the proof because they all use, kinematic invariance in flat space, okay, or perturbation theory and so on and so forth. So at least in my view, I don't think we have any idea why the double copy is true, at least from a field theory point of view, because we don't know even when it's true, okay? Here's what I mean by this, okay? I told you it's true for Yang-Mills and gravity. That's proven to be true. But what if I just added to Yang-Mills f cubed or f fourth or f to the fifth? Okay, there's definitely been work on this, studying it. But if I just give you some generic higher dimension correction which may have come from a string amplitude or may not have, who knows. When does this true? Like, should I always expect it to be true, or is it never true? Is it only true if it's from a stringy theory? What's the rules here? Again, there's been work on this, but there's no definitive answer fully. How does this work in curved spacetime? Okay, as soon as you don't have S, T, and U, as soon as you don't have an S matrix, what is even the statement? Okay, that's where a lot of statements just end because there's no amplitude. So what would we even compute, and what would we even double or square? Is it true? So I've told you it's been recycled into higher loops from generalized unitarity, but I'm asking, could you, like, is it like really an intrinsic feature that you could put into a Lagrangian that'd be true at any loop order? Is it true non-perturbatively? Okay, so of course there's all orders in perturbation theory, but there's also just non-perturbative. Is it true there? Definitely. There's no clue. Roughly speaking, no clue how to generalize it to that regime. Could it apply to classical solutions? We don't know. Okay, so I would say that in all these cases, these ever so slight deformations completely destroy the existing proofs. We just don't know, and there's not even like we know whether that there is a generalized proof. We don't know if it breaks down, if it doesn't break down. We just don't know. And my view is that if you understand something like a symmetry or conserved current, yada yada yada, you know it in all these contexts, right? We understand like things. When we understand something, we get it in all contexts. We shouldn't have to be like, yeah, my proof broke down, so like I don't know, I can't tell you. So I would say we don't understand the double copy, and I would also argue that I think the stakes are super high for a very precise reason. Okay, let's say the double copy was true for all these cases. Okay, that's like totally, I think, a hallucination, and not probably true. Personally, I don't think that's possibly true. But let's say that it was true for all loop orders, non-perturbatively curved spacetime. Well, obviously that would be amazing because it would be a weak duality between quantum gravity, and quantum gauge theory. Okay, so it'd be like a weak version of ADS-CFT. Now, that should sound way too strong. I think it's too strong, and having thought about this long enough, I just don't think that's going to be true. But what I think is very likely true is that it's at least a classically true duality. Okay, and by this, the reason for this is it's classically proven for tree amplitudes. We used it for classical GR. It has vestiges in classical GR solutions. So let's say it's just true for classical physics. Okay, that would still be amazing because it would still be true for classical strong field physics, which would include numerical relativity. So it would tell you numerical relativity, which is not quantum, but is still strong field, non-perturbative gravity, is like the double copy of something. That would be really amazing to me. And I think it's worth pursuing. Okay. Now, what's the point of this talk? That's the setup. The point of this talk is I'm going to give you now an explanation for a subset of these double copies from like honest to goodness basic principles, and we're going to derive it using Lagrangians and like a standard field theory. Okay. Let me just tell you the conclusions of this talk. Okay. The conclusion of this talk is that for a very specific, one of the double copies I mentioned, the ones involving the pion, there is just an explanation for the double copy, which I think is very crisp and actually gave me personally an illumination. Okay. And it's the following. Okay, so the statement of the pion squared gives that, pion times this gives that. There is an explanation, and it's in the end kind of simple. Okay, here's a simple statement. Take a theory with color structure, and I apologize when I say color, I often mean interchangeably with flavor, because to me it's just an internal, index, internal label of fields. Okay, so I'll say color and sometimes just mean flavor. Okay, but that's just what we say in the field. I apologize. But we take something with color structure, like VATA, okay, some field that has a color index, and we replace it with a Lorentz index and turn it into a generator of space-time dependent diffs. Okay, so I'm calling it the diff algebra because V mu of x, partial mu, is a space-time dependent vector, which is generating a translation. Okay, so that's why I'm calling it diffeomorphisms. But just more mathematically precise, I should just call this the algebra of brackets. Okay, the vectors, the algebra of vectors, like the Lie bracket. Okay, from general relativity. Okay, now here's the point. This mapping, of course, preserves Jacobi. Okay, if I had a color Jacobi identity, now I replace it with the Lie bracket, I still have a Jacobi identity. But it's something we can do at the level of fields, and we can apply this to, as I'll show you, equations of motion, in some cases, actions at all loop orders, classical solutions, and for some low-dimensional cases, which is very cool, I think, currents and integrable currents. Okay, so we're going to actually double copy integrability in some low-dimensional models, but it applies more generally. Okay, so I'm basically going to start with the d-dimensional explanation of the double copy for pions. And we're going to do some improvisation after that. So the first thing I'll tell you about is how to derive the double copy for pions from equations of motion. Okay, it's first principles, because we're going to start from things you know from your textbook. I won't tell you like some magic fact about amplitudes that you have to accept. Then I'm going to start generalizing, because once you're kind of cooking with gas, you can apply it broadly. So we'll generalize the curve spacetime, and then I'll generalize it to all perturbative orders in the case of low dimensions. Okay, so that's the plan for this talk. All right, so let's get it from equations of motion. Okay, and again, I said, yes.
If you could go back to the slide where you explained what you're, yeah, this one, great.
Yes.
So if the dimension of your gauge group is D, then will you be working in D spacetime dimensions?
Very good. So in terms of the double copy, you could ask questions about what about the rank of the gauge group and so on. But kind of at the first step, I take the color structure and I throw them out. Okay, if you notice, the first step is I take CS, CT, and CU, and I just discard them completely. Whether you picked SON, SPN, SUN, it didn't matter. I threw it out and I copied the kinematics. So in some sense, the gauge group that you start with is not important.
Okay.
What is important is when you
this
map.
arrow, this color algebra goes to diff algebra. I don't even understand that statement. You explain that. You know, how do you embed? If I've got a V, I give you a VA as a function of X. How will you give me a V mu as a function of X from that? If the
I'll show you. I'll show you in a second. I'll show you in a second. Yeah. If you like, it's a replacement at the level of fields. But let me show you. If you like, yeah, I'll get to this in a second. You'll see in a second.
Great. Thank you.
Yeah. If you see the equations directly, you'll see. Yeah. So first, let's start with the textbook Lagrangian for pions. Okay. So what is that? So here, lowercase j here is the chiral current. Okay. Which is just the usual G inverse d mu G. Okay. In components. And here I've also added an external source for the pion. Okay, so I've added some pi capital J, whose only purpose is that I want to be able to scatter. So I want to be able to like put little pi at infinity and scatter them and see what comes out. So that's why I'm adding a source capital J. And the equation of motion for the chiral Lagrangian is just that the chiral current is conserved up to insertions of pions, which is this capital J on the right-hand side. So in other words, the equation of motion for the chiral Lagrangian is just that the chiral current is conserved, okay, in the chiral limit. Now, there's one crucial thing that I haven't closely litigated yet, which is, well, I'm talking about J. I've talked about G, the group element, but of course, the pi field lives inside G. Okay, so we're used to taking very commonly like an exponential mapping, e to the I pi over f pion equals G. Okay, that's nearly standard. But of course, there's many other choices of embedding of the pi field inside the group element. You could pick this Cayley representation, which is also a unitary or also a group element, or you could pick any other choice. Okay. Now you could ask which one of these is right. And of course, none of them is right. They're all just different choices of embedding. Like there's not a right embedding of pi into G. Okay. Now, if you think about that, famously, it means that there's a big redundancy. Okay. Depending on whether I choose exponential or Cayley or what have you, my Lagrangian as a function of pi will be different. My vertices will look different. Everything will look different. But of course, if I compute on-shell things, it won't matter. That difference in field redefinitions always cancels out, right? That's the usual feature. We integrate over fields. So as long as we compute some kind of gauge invariant, coordinate invariant object, like a non-shell scattering amplitude, it won't depend on that choice. Now, what does this mean? So this means that let's say I wanted to just like get some Lagrangian that has double copy as a symmetry. Okay, that's basically the goal here. I want to write a Lagrangian or some formulation where like double copy is like just staring in the face. Like there's the color, there's the kinematics. I can clearly swap them and like, duh, it's just a Z2 of the theory that's hidden in some particular way of writing Lagrangian. Well, you could just try to hunt for like some appropriate choice of pi. You know, keep looking for some choice of pi. You know, try this, try that. But you obviously is like an infinite well of possibilities. It's a very bad way to try to look for some double copy compliant Lagrangian, double copy manifesting Lagrangian. A much better way is to use a more invariant degree of freedom to represent your physics. And what I'm going to say is to do that, we should use J, the chiral current itself. Okay, so the idea is let's now reformulate the chiral Lagrangian in terms of J. Okay, like not treating pi as the degree of freedom, but the chiral current itself. which is kind of more invariant because it's a conserved current. What do I mean by that? Well, here's what I mean. Here's a first order formulation of the classical NLSM, which is equivalent to the previous slide classically, okay? And here's what I mean. So B is just the equation of motion. I'll just take that as input. It's the equation of motion that we get, so I'm taking it as my starting assumption, okay? But rather than start with the embedding of pi inside J and all that story, let me instead use equation A, okay? So equation A, what does it say? Equation A is the statement that J is flat if viewed as a connection. Okay, if you just squinted at this and you thought that J was a gauge field, you'd be like, oh, that's a flat connection. This is a non-abelian flat connection. Of course, that's what this is. If you fix this condition, it implies that J is pure gauge, which if you like, cuts out everything in J, removes everything in J mu except for the group element G. Okay, basically, it's like a Stuckelberg type thing. We're like introducing the pion by demanding that J is pure gauge. Okay. Now, so this is the pion being born implicitly through this constraint. Okay. Now you could ask, how is pi embedded in G? Is it exponential? Is it Cayley? Doesn't matter. And the whole point of this is I'm not even going to tell you how it's embedded. It's irrelevant. I'm not going to care. The point is this implies and sculpts out everything from J except the pion field. So A and B together implicitly define the chiral Lagrangian here. Okay, this procedure was done in the past, I should say, by Freeman and Townsend in 81, where the central question was, well, we know how to dualize a an axion to a two form, right? A U1 axion to a two form. It's very simple. Just Hodge dualize it. But if you had a non-abelian axion or a pion, how do you do that? And they essentially use this kind of trickery using this kind of field strength flatness condition. Now here's the leap. Okay, so the leap now is A and B define my theory, at least classically, and in perturbation theory. So let me combine them and think about this as a theory of the chiral current. Okay, so take A and B and just take this combination of them, and you get this equation of motion. Okay. Now, what does this equation of motion look like? If you just handed this to someone would say, oh, this is an equation of motion for a non-abelian vector, J, which has a Feynman propagator, a 1 on p squared propagator. It has kind of a strange external source that's derivatively coupled. Okay, that's fine. And then it has purely three particle interactions. Okay, because there's a JJ here. It's quadratic in J in equations of motion, which means that if you thought of this as coming from some theory, it'd be a cubic interaction. Okay. Said another way, if you perturbatively solve this equation of motion in the presence of a source, you get tree diagrams that are cubic. Okay, so the Feynman rules, if you like, for this equation of motion are cubic. There's some set of external sources, and the degree of freedom is now the chiral current. Okay. Now let me just mention an amusing historical thing, which was when I gave a talk about this at the 100th anniversary at the Niels Bohr Institute in Denmark, and amazingly, Polyakov recognized immediately this formalism as something that appeared in a paper by Slavnov in 1970 called a gauge invariant field basis independent version of chiral perturbation. Okay, so basically just use the chiral current as the degree of freedom. Of course, they knew nothing about the double copy, which is what my angle is here, but this idea of using a more invariant object has been done. Okay. Now, what's the idea here? So the idea is we're going to treat J as the degree of freedom, compute amplitudes with J, compute everything with J, and we're going to see the double copy pop out. Okay. But before I do that, let's go roll back slightly, okay? Because we don't care about scattering chiral currents. We care about scattering pions. That was the original point. Okay, the point is we need to scatter pions. And you might worry, well, your degree of freedom isn't the right one, but it turns out it's okay. Why? Well, J mu is d mu pi at linearized order. At lowest order in pi, it's d mu pi, up to ... which are nonlinearities in the pion. Okay, now field definitions, like going between exponential and Cayley and all these things, that changes the ... Okay, so these ... will change. Okay, so if you're off shell, this would all matter. Okay. But what we're going to see crucially is when we go on shell, LSC is going to kill all those ... pieces famously. But well, wait a second, we'll see how that happens. But the point here is that J is related to d pi plus stuff, which means that I can formally invert this equation to write pi in terms of J. Okay, so the idea is just hit it with a reference Q. This could be like an axial gauge type reference, some reference vector. Here, Q partial, if you like, in momentum space is just Q dot P for P flowing into J. Okay, but that is you can formally invert J to pi. The linearized J is the pi. What this means is that the 1-point function for the pion is contained in the 1-point function for the chiral current. Okay, that's sufficient to claim victory for the following reason, which is that if you want to compute the 1-point function for the pion in the presence of sources, that is precisely the endpoint pi and amplitude. Okay, so famously, if I solve an equation of motion for a field in the presence of sources and I perturbatively solve in order by order in the source, I get the tree amplitude S matrix. Okay, in other words, equations of motions are generating functionals for tree amplitudes, famously. So I just have to differentiate with respect to J. The point here is the 1-point function for pi is the 1-point function for the chiral current. So I just have to differentiate the 1-point function for the chiral current. So the upshot is, if you solve the equation of motion for the chiral current, it contains all pi and amplitudes in this simple formula, which basically boils down to dotting into this external polarization. Crucially, the dots, the extra field basis dependent stuff, all is truncated by LSZ, as is usual. LSZ truncates these nonlinear corrections, so we can just not care about them, which is precisely why physics is invariant under field redefinitions. What's the upshot? Okay, that's all kind of a lot of technical stuff, but the upshot is that there's just a set of Feynman rules that these equations of motion give you that compute pi and amplitudes. Okay, so in other words, if you take this as the definition of the theory, because it's equivalent, I derived it, and you extract the pi and amplitudes from it, these are the new Feynman rules for pion scattering. Okay, so I'm saying the following: you have a spin 1 vector field. Okay, doesn't look like a pion, but secretly contains all the same physics. It has a Feynman propagator because of the structure of the equation of motion. It has a 3-point function, which is here. And then it has some external polarizations that have derivatives and some weird one on p.q's. Okay, but it's just a simple set of explicit Feynman rules. What I'm saying is, if you just take this, draw all diagrams and connect them, you literally get these scalar pi and amplitudes. The same answers you would have gotten using the chiral Lagrangian. Okay.
Of course, is this true only at tree level or also at loop level?
This is true. Actually, turns out it's true at one loop, but let's for the moment only commit to it being true at tree level. I've only proven it for the classical equations of motion, so it's only true tree level. Yes.
Okay, thank you.
I'll get to loops a bit later, actually. Yes. But already there's a huge difference between this and the usual way we compute with pions. Okay. The usual way with pions, we have a chiral Lagrangian, we have pi to the 4th, pi to the 6th, pi to the 8th, all even point pion vertices to infinity, right? Okay, you have to do a lot of work to compute the 10-point pion amplitude. You got to get all the vertices. Okay? Now, this completely obscures that structure. Okay, there's only one vertex. There's a single cubic vertex, which is the one I have here. Okay. Second, it obscures G parity, pion parity. Okay. In the absence of a WZW term, there's a parity in the chiral Lagrangian, which says that pi should come in even powers, which means that all odd point amplitudes are 0. Naively, this is a 3-point coupling. You'd be like, oh, wait, you have a 5-point, 7-point amplitude. Turns out all 0 on shell. Okay, so it's spurious. So this obscures that parity, but of course it conforms to it because it gives the same physical answers. So all the odd point amplitudes are 0. Okay, so that's the second thing it obscures. The third thing it obscures is Bose symmetry. Okay, that's the most fascinating of all these. Okay, normally if I give you Feynman rules derived from an action, there's manifest Bose symmetry of the vertices because you got it from an action. But famously, if I give you equations of motion and perturbatively solve them, they do not have Bose symmetry intrinsic. Okay, this happens in the Navier-Stokes equations. Famously, the Navier-Stokes equations are not trivially the Euler-Lagrange equations of motion for some Lagrangian that depends only on the velocity field. And the way you see that is that the Navier-Stokes vertex is not permanvariant. Okay, it has like a special direction of flow towards, in other words, the equation of motion itself has like an extra label on it. This has the same feature. Okay, so in other words, it's not manifestly Bose invariant, but of course the final answer is Bose invariant. Okay? It obscures that. Okay, now that's all the stuff it breaks. The one thing it doesn't break and makes nice is color kinematics development. And here's what I mean by that. It just holds off shell. Okay, so that kinematics code, yes.
Sorry to interrupt, but
yeah.
You wrote down an equation of motion, but it's something like, from what you're saying, that you're not planning to write down an action that generates that equation of motion. Is this right?
No, at present for this classical story, no, but I will go to an action towards the last third of my talk. But in general, I would say in general dimension, I do not yet know how to write a full Lagrangian for this at all loop order. I can do it at one loop, but not at all loop order. So right now you should say this is a purely still classical equations of motion statement for still classical equations of motion statement in general D. For special D, I can do more, but not in general D.
Okay,
we'll still see that it teaches something amusing them. Yeah, which we'll get to in a second. Yeah, cool. Now, classically, again, for tree amplitudes, what does this tell me? This tells me the following. Just compute the 4-point off-shell 4-point function of 4 chiral currents. Okay, so this could be some, like 50-point on-shell amplitude, but you're like diving deep inside it, inside some sub-diagram, which is off-shell. And the statement is if you just compute the NS, NT, and NU, there's 3 sub-diagrams off-shell. Only condition here is momentum conservation, which is true off-shell in addition to on-shell. You find that they exactly sum to 0. Okay, so the point is like there's no external on-shell condition in play here. This is just an identity. Okay, so there's a kinematic Jacobi identity, which precisely mirrors the color Jacobi identity, which is off-shell. That is to say, in any diagram you draw in this formalism, it's basically a tree diagram with all 3-point amplitudes, every sub-diagram automatically satisfies the Jacobi identities that I was telling you about before. Okay, this is the formalism that manifests it explicitly. Okay, now, but why? Okay, I'm still showing you just equations. What's the physics for why it's happening?
Sorry,
well, the way to see it, yes.
Could I back up one minute before that? The fact that your amplitudes are permutation invariant, is that enough to establish that even though you may not have it, that there exists an action that generates these equations?
Oh, so you're saying because the final answer is perm invariant, is that sufficient for me to know that there exists an action that generates rules? If
there was an action, it would imply permutation invariance.
Yes. Yes.
So I was wondering whether the reverse was also true, that one can demonstrate that whether or not we know what it is, there must be an action because the answer is permutation invariant.
Good. So I don't think we can guarantee that because the on-shell final amplitude is perm invariant, that there exists an action that is perm invariant that has color kinematics duality. Right. So in other words, we know that there's an action that gives us answer. The chiral Lagrangian in standard form is perm invariant and gives us answer. But you're asking I'm demanding a second condition, which is it also manifests color kinematics duality as a symmetry. And that I have no reason to believe is consistent with perm invariance. So I would say I don't think it's guaranteed. Yes.
Okay. And just backing up, just looking at the action that need not be invariant under color kinematic duality, would that action in general be non-local when expressed in terms of this J count? If you just rewrote the action of phi in terms of J.
Good. It doesn't have to be non-local. You would kind of expect it to be because that 1 over p dot q. But I'll show you a version in low dimensions where it's totally local and it has a name. It has names that was named 40 years ago, 50 years ago. So it doesn't have to be non-local. In general, though, in general D, maybe. Again, I haven't succeeded in writing a Lagrangian for the full loop story in general D. One loop is still local. But that's a very good question, which is, should you somehow require to be in like some kind of light cone gauge or some kind of intrinsic sense of like having integrated something out or added auxiliaries? I don't personally know yet. I don't know yet. Yeah.
Thank you. Yeah.
Sure. Good. So why did those happen? Well, we can see it if we just like look with our eyes. Okay. So let me introduce a theory that shows up all over amplitudes called bi-adjoint scalar theory, BAS. Okay. It's a very simple theory. It's a theory of a scalar with a single cubic interaction. Okay, it's phi cube theory. But this scalar has the feature that it has 2 colors. It has a color and a barred color. Okay. It's not gauged. It's really an internal flavor symmetry. Okay. But it's just a phi cube theory where the phi has an adjoint of one SUN and an adjoint of another like barred SUN color. Okay. So it has 2 adjoints. It's bi-adjoint. Okay. This is its interaction. Okay. Now, why am I bringing up this theory? It's kind of the skeleton of all double copies. Why? Because it has one color, which we're always going to interpret as the kind of usual color. For instance, in Yang-Mills, I think of the color as, let's say, the ABC type indices. Bi-adjoint scalar theory is a way of kind of abstractly thinking about the kinematics, where the barred indices, they look like color, but I'm thinking of them as kinematics. Okay, it's really kind of committing to like color is kinematics picture. Okay, but of course it's its own fine, at least in perturbation theory, fine theory, it's phi cube theory. Okay, so bi-adjoint scalar theory is just a phi cube theory, really nice, well-behaved, we understand it. Again, modulo vacuum and other things, but it's a perfectly well-defined in perturbation theory. And the chiral Lagrangian is what I just described to you, written in terms of the chiral current. And then we just look at the 2 by eye. Okay, you can see that there's a mapping between these. Okay, and this is what I meant by the arrow. Okay, the arrow mapping. Phi AA bar, that A bar is some color structure, it could be an SUN or whatever. The point is just take whatever that color structure is, just throw it out, chuck it, okay? And replace a bar with mu, okay? It's a mapping between fields in the same space dimension. So these are both d-dimensional theories, but I'm just in some sense, pruning away the barred color and replacing it with the mu index, okay? So that's the rule here. Take a field with a barred color index and replace it with Lorentz indices. The second rule is f a bar, b bar, c bar. That should be the color structure constant in the barred side, but that should be now kinematics. And what it tells us is we should replace it with some differential thing. You might be like, what is that? What could that possibly be? Well, it turns out it's very simple. It's precisely the structure constant for the Lie bracket, okay, for the commutator of vectors. Okay, so here is the specific operation. Here I've gotten rid of the bars because I don't want to drag those a bars everywhere. So just imagine VA. I have some object where I have color structures A, B, C, and so on, and FABC that I want to replace. I literally just bleach them away and replace them with a mu index and replace color structures by this replacement. Okay. It maps, this is mapping the color algebra, like a color symmetry I had in my theory, chucking it and replacing it with these differentials and thinking of it as a one spin higher object. Okay. So this is just computing that Lie bracket. Okay, just to be very explicit, commutator of two space-time dependent diffs gives this, and this is the structure constant. Okay, that's a replacement, and the external sources just get a derivative. Okay, so this is the mapping. So just do this to a theory, and this is the field level double copy. If you have equations of motion. Okay, so given equations of motion with a color structure, do this, and you will get equations of motion in a new theory. Okay, let's see how that works. And in fact, let's apply it. Okay, so we're gonna do that the first time this has been done before with currents. Okay, I told you this is the mapping, so I can take anything with fields and I can double copy them. First thing that you should copy.
Sorry.
The second thing you should copy
Yeah.
after the field itself is a current. Yes, was there a question?
Yes, sorry. So this map is an abstract map in the sense that if I had a phi a bar as a function of x mu, I would not from that be able to get your other thing, because this a bar runs over some number of values which you've not specified, and this
very good. At this level, it's an abstract mapping. At the end of my talk, I will show you the direct mapping in low dimensions, where in low dimensions, it's a very precise action on the gauge group that will turn it into the diffs. But absolutely, in general, you should think of it as an abstraction of like a replacement. It's a active bleaching of the old theory and replacement of new one, but one that is manifested if you write the equations of motion in this way.
Okay,
but actually later on, I'll show you a even more direct mapping. The last thing I'll tell you is the direct mapping, actually.
Okay, thank you.
Yeah, all very good questions. Now, let's double copy a current, okay? The first thing you copy is the field. Second thing you copy is a conserved current. What happens? Okay, so this phi cube theory I wrote here has two global symmetries because it's got two adjoint symmetries, right? So I have two conserved currents. So let me just take one and double copy it. Okay, so here's another current for that flavor symmetry. Okay, it's some internal flavor / color symmetry of this phi field. Let me apply that mapping. So what does that mean? That means I take the phi's and I take phi AB, I send it to JA new. Okay, so I sent the B bar to a new index. And I replace the structure constant with this differential. And I get a new current, which is something in the chiral Lagrangian. It lives in the pion theory. Okay? And I predict that it should be conserved. Okay, it's bilinear in the chiral current. And you can just check that d mu of this thing is 0. Okay, so we properly constructed a conserved current. In fact, you can, if you've heard about something called the fundamental BCJ relations, you can derive them this way. Now, you should now left with a puzzle, at least briefly a puzzle, that we're confused about for a couple of days. Like, wait, what is this? Like, this is a conserved current in the chiral Lagrangian. I thought I knew all of them. Like, how can there be another object? Okay, and of course, the answer is in just looking at this thing, an object with two indices, two spacetime indices that's conserved. Feel like there's no room for any more. Well, as you can imagine, it's directly related to the stress tensor. Okay, so it turns out that this like double copied current, which is precisely the thing that mandates the kinematic Jacobi identities, like literally the kinematic Jacobi identities are dictated by this thing's conservation law, is just Bach stress tensor plus improvement terms. Okay, I can show this explicitly. So in other words, there is a conserved current for the kinematic Jacobi identities. It's just a descendant of the stress tensor. Okay, and this I love this result because it at least for me illuminated a confusion I've always had about color kinematics, which many people immediately have when someone says kinematic algebra, which is, what does that mean? You took color, you replaced it with kinematics, but that's like saying there's some symmetry that's kinematic dependent. And there's no room for that. Coleman Mandula told us there's no room for that unless we go to a gradedly algebra. There's, of course, we know how to do that. We extend things, but in the kind of conventional picture, there's no kinematic symmetries that could exist. But the point here is there is no kinematic symmetry. There's only a conservation law because it's the same as the stress tensor conservation. All the charges corresponding to this are actually zero. So there's no symmetry action that this corresponds to, but there is a conserved current which mandates the structure. And it's not a new one. It's the old stress tensor. Okay, so it's kind of the most satisfying way that everyone can be happy. There's no kinematic symmetry, but there is a kinematic current. It's just a derivative of the stress tensor. Okay, so that squares, and as it's nicely consistent. Okay, but this is an example of like, this is me double copying fields and currents. Now let's just apply this to everything we know. Okay, so what do I mean? Well, let's just take anything with an equation of motion with a color index and just double copy it and just see what comes out. So again, this is what I already said, but let me recap it. I have biadjoint scalar theory. This is the field. This is its equation of motion. If I double copy it, it sends it to a new object where the A bar goes to Lorentz index and so on. Okay, that's what I just did. Okay, let's do it a second time. What do I mean by second time? Well, I can start with the Chiral-Lagrangian. I've chosen to write it in my formalism here with J, but you could do it any way you like. But you can write the NLSM this way, and there's still a residual flavor structure because NLSM still has flavor. So what do? I just do it all again. Take J mu A, replace it with J mu bar. Okay, just do it the same thing again. Replace both internal symmetry labels with kinematics. You get this thing, which of course looks very reminiscent. You should think of this as the double copy at the level of equations of motion. I've like squared the equations of motion. This is like squaring those kinematic numerators at the level of an equation of motion. And it turns out that this is this is not a known formalism, but this is exactly equivalent to the special Galilean theory, the Galilean theory I mentioned before. So if you just solve this cubic set of equations of motion, you get all the amplitudes in that Galilean theory. This is, if you like, a field level description of this double copy procedure. Okay. Now you can also do things even more exotic, okay? Let's bring Yang-Mills back in. I haven't mentioned Yang-Mills, but of course Yang-Mills has color in it, okay? So for instance, I could take Yang-Mills, which I think in a first order formulation has a field strength, F mu nu, has a gauge field, A mu, and then, I have a field strength and then the field equations, okay? But there's a color. There's an ABC, there's an FABC. So let me do the replacement. Okay, that means I take A and F and I replace their color indices with a new barred Lorentz index. Okay, this is highly exotic. Okay, but you do this because that's what the instructions tell you to do, and you get field equations that, if you squint at it, look just like Yang-Mills theory, right? If you didn't look carefully, you'd be like, oh yeah, dA plus AA, dF plus AF, but they're not Yang-Mills theory. They have derivatives and no color, and this is precisely Born-Infeld theory. Okay, you can check it up to 6 point, but the point is, this is a version of Born-Infeld theory, which does not have an infinite tower of photon interactions. Usually Born-Infeld theory has F's, F4, F6, F8, and so on with very specific coefficients. This here is a pure quartic theory because Yang-Mills started quartic. Okay, so that is, I took like quartic equations of motion, I double copied them. So this is an entirely quartic version of Born-Infeld theory, which is correct. Okay. I should mention one thing kind of amusing. I'll just mention offhandedly. I'm like 95% sure that the higher form symmetries should double copy appropriately, because the kind of starting theories here are the Chiral-Lagrangian and the Yang-Mills, which of course have a zero form chiral symmetry and a one form ZN center symmetry. And Born-Infeld, like any theory of just a field strength, has a continuous one form symmetry. So I'm very strongly suspect that the higher form symmetries actually can emerge from the double copy. You can see it emerge from this kind of relation. Okay, that's all I want to say about the equation of motion story. Let me move on. Now that we kind of know what, yes.
Can I ask about the previous slide? I got confused about it. So sorry. First question, when you say Born-Infeld, do you mean U1 Born-Infeld?
Yes.
Sorry, you said this, but I missed it. The U1 Born-Feld that I'm familiar with is just a gauge field with one index. What in that context is the gauge field with two indices?
Very good. Yeah. So usual Born-Feld is like square root 1 plus f mu nu, and it's just abelian. This has two, a mu mu bar. Just like, and you should think of it in the following way. If we go back to this chiral Lagrangian case, this J has a mu index, but the pion didn't have a mu index, right? This is the current that's associated with that pion. This is like d mu pi, okay? J is d mu pi. In the very same sense, in Born-Feld theory, this A is actually d mu bar of the Born-Feld photon. You should think of it that way. This is a formulation for the derivative of the photon in Born-Feld theory.
And the mu bar is just another spacetime index.
It's another spacetime index. That's right.
It's on the same footing as mu.
Yes, same footing. Yes,
oh.
It's the same footing, except index factorization kind of happens automatically. Like, so but it's the same space-time. It's the same space. Yeah, it's all the same stuff, indeed.
Okay,
but you can see that the mu bar never comes in it doesn't come in contact with mu, right? Because it never gets contracted with the mu. So you could treat it separately if you wanted, in kind of a double field theory type picture. But here we can fix general D, and mu bar and mu are the same dimension. Yes.
Yeah, just a couple of more questions just to understand.
Yeah.
You said that this was, if I understood you right, you said that this was a quartic rewriting of the usual Born-Feld theory. Is that right?
Yes, that's right.
So it's some field redefinition that takes these infinite number of terms and makes them all quartic.
Right. So I don't know what the field redefinition is. There may not be something as simple as a local field redefinition, but it is certainly physically equivalent. In the same sense, maybe there's a field redefinition that gives you this chiral current, like literally explicit, like maps pi to j. But I'm just going to say they're equivalent. I think having a local field redefinition that's sensible you could write down is asking more, but definitely I'm saying it's equivalent. So I'm saying this is equivalent to Born-Feld, but it's a quartic representation of it. Yes.
By equivalent, you mean it has the same S matrices?
Same tree level S matrix. Yes.
Yes. Okay. And now I'll ask the stupidest of all the questions. Please forgive. But it felt like at the beginning of the talk you talked about how when you replaced the color in Yang-Mills with the kinematics, you got gravity. It's confusing me that you're doing something that seems very similar but getting Born-Feld.
Very good. So let me explain what I'm doing in the context of the first slide. So in the first slide, we took Yang-Mills, which had color and kinematics. Okay. And we took the color, threw it out, and replaced the kinematics with the kinematics of Yang-Mills. Like I threw out C, and I took a second copy of N in Yang-Mills. That was N Yang-Mills squared. That gives gravity. Yeah. This is a different operation. This is taking the color of Yang-Mills, throwing it out, and replacing it with the N, the numerator of pions of another expression. So that's why the N's here are not N of Yang-Mills squared, it's N Yang-Mills N pion. And that's what this double cut.
But could you have done the same thing with just N Yang-Mills?
With two Yang-Mills?
Well, no, to get gravity, could you have replaced this without replacing the color with the N of pion instead of replacing it with N of Yang-Mills at this field level to get gravity?
Very good. So the question is, what is the analog of replacing the kinematics with Yang-Mills's numerators? Not pion's numerators, but Yang-Mills. Yes. And that is still an open question. Yeah, so like the analogous formalism of like throw out your color and replace it with kinematics, not of the pions, but of Yang-Mills itself. I thought that I do not know yet the crisp way of doing that. It's much for various reasons much more complicated than this, it seems. But there is no formalism where someone has a field level where it's like do this replacement. It's not the diff algebra. It's like, whatever, something more complicated, like the gauged Poincare algebra, something you might imagine. There's no explicit construction like that, sadly. It does exist for self-dual Yang-Mills. So for self-dual Yang-Mills, you can go to self-dual gravity. And it's actually a similar diff invariance. This was work by Donald O'Connell and Ricardo Montero a long time ago. Very cool. Of course, self-dual Yang-Mills has some kind of trivialities, integrable, and etc. Maybe the surprise is that same kind of diff structure applies for pions in general D, which are not like very symmetrical in any sense. But yeah, I that's an open question. Like, just what is the field theory level kinematic algebra for Yang-Mills is not an answered question. Yeah.
Thank you so much.
Sure. Thank you for that question. That's a good question. Good.
Sorry, just one question about this. So in the you said how in the biadjoint, if you did these replacements of the FABC and changing A to mu, you get NLSM, right?
Yeah.
But one could also do another replacement and get Yang-Mills out of the biadjoint as well, right? With the FABC times your fields. You had a rule for going from FABC.
Oh, good. Yeah.
product
So like
fields.
you're saying, could I have taken this top line here?
Yeah.
And if I took FABC and replaced it with the kinematics of Yang-Mills, I should get Bordenfeld in a second way. Yes, but I don't know what to replace FABC with, because as I was just saying to Shiraz, I don't know what the algebra for the Yang-Mills numerator is. I know what it is for pions, it's stiff. But for Yang-Mills, we don't have something nearly as explicit. So indeed, though, if you or someone can figure out, like, here's the simple mapping, FABC goes to this other thing, then you could apply it to this top line, and you would get Bordenfeld in yet another representation, like yet another way of doing things. Indeed, yes. I should say also, here's another thing you can do. Rather than taking my chiral current representation, you could take your standard old like NLSM with pi a, like regular old pion. That has a indices. You could write out all the structure constants for the chiral Lagrangian and standard formalism and with FABCs and just do the replacement at the equations of motion level. You'll also get yet another representation of the special Galilean. So like, just do whatever you want. Just do this mapping. The point is, it's not about your field basis. It's about the replacement of color with kinematics. Yeah. Cool. All right. So very good. Now the point here is we as I was saying, we're cooking with gas. We know the mechanism, and it's a really simple one, and it based on this very trivial point, basically. If you start with a theory that has a color structure, anything nice about it that you could check, like a Ward identity, conserved current, this or that, it depends on the Jacobi identity. That's essentially all it cares about. It doesn't care detailedly about whether it's SUN or SON. It cares about the broad features of what color implies. So anti-symmetry of the structure constant and the Jacobi identity. The point here is if you replace it with something which is just as good, which satisfies all the same identities, all those checks will still pass. That's basically the idea. Okay, so Jacobi still holds, you're still anti-symmetric, so we're good. Okay, so and we're not replacing it with another gauge group, we're replacing it with something kinematic, which is the kind of more interesting part. But that's why you could expect this to work. Now, once you know this, you can now go, okay, we're going to improvise now. We're going to like move outside of flat space on shell. Maybe I didn't say this clearly before, but the whole point was to move outside of the amplitude story now that we kind of know what to do. And let me tell you the story in curve space. Okay, so I need to accelerate a little bit, so I'll probably do this section super fast. Apologize for that. But here's the idea. First, we just have to know what to compute. Okay,
sorry,
we don't have
Cliff, just to let you know that we don't have very stringent constraints from our side.
Oh, cool. Okay, if that's true, then maybe I won't fly too quickly. Again, I don't want to keep people too much, but I can go on at length. So I'll do it. I mean, I'll maybe do a little faster, but I won't rush through it. No, thank you for that comment. Okay, now as soon as I'm not in flat space, we immediately have a puzzle. Like, what are we even computing? Okay, right. If we don't have momenta, so we don't have like standard kinematics. We don't even have amplitudes. Okay, we're like de Sitter space. We don't have asymptotic states. We're in big trouble. Okay. So the zeroth order question is, what is the object that is in play? And at least in my view, I think this was like, at least the zeroth order basic idea was answered in a paper by Radu Roybon. I should also mention papers by Sebastian Mazzara earlier also. And basically the question was like, what is the object that we should expect to be kind of nice and amplitudes like? Okay. And here's what I think the story is. Okay. And let me just start with flat space. We're going to draw a bunch of analogies, column by column. In flat space, we have on-shell scattering amplitudes. We can think of those, let's take tree level here as before. We can think of those as solutions to the equations of motion in the presence of plane wave sources, a sum of plane wave sources. Okay, that's what a tree level amplitude is. The plane waves are the linearized solutions at infinity. Okay, so the idea is like we solve the linearized equations, we get a bunch of plane waves, we add a bunch of them as our source infinity, and then we kind of perturbatively solve for the solution in the bulk. Okay, that's me just saying solve equations of motion. Okay, delta function is important because it represents momentum conservation, but also you can think of it as a contact endpoint function for the endpoint correlator. Okay, that's another way of thinking about a delta function, and the kinematics are momentum. Okay. Now, if I just kind of extrapolate those to the case of ADS. This is basically the contents of this paper. This very cool paper by Radu and friends. Well, the solution to the equations of motion you can think of as the bulk boundary propagators. The onshore amplitudes these are analogous to boundary correlators. The delta function is the contact correlator, and the momenta are conformal generators. Okay, so they're the isometry generating, operators in the space. So this is their story. I'll tell you it, but in more generality, because our work was basically realizing a dumb thing, very simple thing, which is that all these statements apply more broadly, not just to a maximally symmetric space, but to a symmetric space, okay, which is a less special class of spaces. That is to say, a symmetric space is any space where the Riemann curvature is covariantly constant, okay? But that isn't to say it has a maximal number of killing isometries. Okay? And we define these things, yes.
Could I ask, in ADS, these correlation functions we compute sometimes have these bulk point singularities whose residues are actually bulk S matrices, or at least class-based bulk S matrices. So in some sense, it feels to me, if you think of ADS like a box that regulates flat space, it seems to me that the correlation function contains more than the flat space S matrix, because the correlation function is some analytic function whose singularities have residues which are the S matrix, but there's the rest of the correlation function. So it feels a little bit to me, maybe this is silly, but it feels a little bit to me like the correlation functions has the S matrices, but is a little more.
Right, I agree. I think I agree. Like, basically, the fact that you extract the flat space S matrix from the one on energy pole already tells you there's other stuff that's not the energy pole that's floating around. So I'm with you on that. There's more in there. It's somehow more off-shellish, but at least for this talk, I'm only going to focus on. Well, I'm not even going to be doing that construction, I should say. I'm not localizing the energy pole. I'm not trying to extract the flat space amplitude from it. I'm really just looking at the, if you like, full-on boundary correlator. And that information is in there. So indeed, I'm not actually, the statement here isn't that I'm taking an ADS correlator, going to the one on energy pole and extracting the amplitude. I'm not doing that. I'm doing a different thing. And Radu is doing a different thing too. But I certainly agree in the spirit of it, which is that seems like there's more stuff in these objects, which is kind of interesting also.
So you're going to tell us that this double copy applies to this larger object?
Yes, that's correct.
Yes.
Yeah. And in fact, beyond ADS. Okay, so what do I mean precisely? I'm going to define something called an on-shell correlator later on, but the idea is basically the following: you define some set of linearized solutions to a wave equation, your theory zero coupling. You can define a contact correlator, and you can define what we call isometric momenta, but just a fancy way of saying kind of natural kinematics for the killing isometries of your space. Okay, so it's more general. This can apply also to de Sitter if you care about coefficients, the wave function of the universe, and so on. But I'm going to do it very broadly. And again, okay, so there's a whole third part of this talk I want to get to, so maybe I'll go through this a little quicker. Okay, so a symmetric manifold has a set of isometries that are parameterized by these killing vectors, which are labeled by capital A. Okay. The only point here is we're going to do kind of almost semi-standard thing, which is just write everything we can in terms of the kind of killing vector index. So kind of label our directions on the manifold in terms of those isometries. Okay, so that's the mapping. It looks a little bit like a tetrad, if you like, but it's one that's based on these killing vectors. And the kind of mechanical level, we're taking mu nu spacetime indices and writing everything we can in terms of killing vector indices. Okay. We can define a Lie derivative, which is just this. This is my shorthand for it, dA. But the kind of key difference from flat spaces, of course, the isometries here, unlike translations, are non-commutative, okay, because there's some killing structure constant. Okay, now, as is maybe somewhat well known, the nice thing here is that we can recast lots of things in terms of these Lie derivatives. So, for instance, the Laplacian acting on a scalar is just the killing Casimir acting on the scalar. Okay, this is just an identity here. Other types of derivatives like this, we can write in terms of Lie derivatives. Okay, so the idea is like, feel like what was partial derivatives in flat space, which are secretly, translation isometries acting on fields, I'm like lifting to the isometries of whatever space abstractly we're talking about. So any theory with phi, d phi, we can write it in this way. Now, we can also define external wave functions, okay? What do I mean by that? I mean something which is annihilated by the killing Casimir. In flat space, this is things annihilated by the Lambertian, okay? E to the IPX is annihilated by box. In ADS, these would be objects that are annihilated by the conformal Casimir, okay? The point is we can write some space of functions like this, which are labeled by some external label, pi. Okay, obviously in flat space, this is the momentum pi, but it's, oh, okay, I'm sorry, I'm running out of batteries here. Let me, but there's some space of functions like this, and there's an analog of momentum conservation, which is that if you act with the killing isometry vector on x, the coordinate, and also on the boundary data pi, then it's 0. Okay, basically the isometries generate new solutions from other solutions. Okay, this is momentum conservation, quote unquote, but in terms of a general isometry. Okay, so we call this isometric momentum for the obvious reason that it looks like on-shell conditions. Okay, this is like box is 0. This is like total momentum conservation is 0, except the d's don't commute. Okay, we can define an analog of a delta function, which is just a bunch of these linear solutions strung together at a point and then integrated over x. But the upshot is that we have like a delta function. We have momentum conservation, which is a statement that if you apply the killing isometries to every single boundary data point, then it's 0, cancels in the end. And we also have that Casimirs are annihilated, annihilate our external states because we've defined solutions that satisfy that. So that's our on-shell condition. The key point is that abstractly, we can now just think of this script D as like P. DI is like PI. It's square, annihilates external states, and it sums to 0. And it's non-commutative. So basically, there's just a non-commutative momentum. We can also now do LSZ. Okay, what is LSZ? Well, in flat space, of course, we take a bulk correlator. We hit box on the external legs, and then we dress it with e to the IPXs, and that's the amplitude. Okay. In ADS, we can think of boundary correlators in a similar way. We can think of a bulk correlator, okay, x in the bulk. We can hit it with box to like amputate those bulk propagators. And then we reattach bulk boundary propagators, which is psi, to string them to the boundary. Okay, so it's like start with the bulk object, strip off its bulk propagators, and put on bulk boundary propagators. Okay, so this is a boundary correlator. But the point here is you can generalize this to like an abstract correlator in a more general set of spacetimes. The point here, though, is that there's now a simple differential representation for the amplitude. This was pointed out by Roybon in ADS, but is more general, where we have a contact correlator, and then this A, which is a function of these differential operators, these lead derivatives, essentially. That's what the D's are. They're lead derivatives essentially acting on the boundary data. Okay, let me just show examples. The kind of only key point here is that all the amplitudes, which are really on-shell correlators, and also Witten diagrams and coefficients of the wave function universe, they all look exactly like amplitudes in flat space, except p-squared is replaced by inverse Casimirs of the symmetry group. Okay, it's kind of the natural obvious thing. Admittedly, this is a little formal because that's like 1 over Casimir. I'm clearly not worrying about epsilons. In the case of ADS, I'm thinking about Euclidean ADS. So it's a little bit formal, admittedly, but this is an expression that at least exhibits all the same parallel structure as flat space and is the answer. You can do it for derivative. Yes. So there's a question?
These operators don't commute, right?
No, they don't commute. Oh, sorry. The Casimirs commute with each other, actually. Sorry, I should say. It's very cool. The Casimirs commute with each other if they contain or are contained within subsets of momenta. So if you like factorization channels that are consistent, commute with each other. So if you had like P1 to Pn, giving you a Casimir, and you had some subset of those P's in a Casimir, those would commute. So it's actually kind of interesting. Factorization is learned about through the commutation relations of this. But in general, they're not commutative, which means to solve for this, you write an equation of motion and solve it keeping track of the order. Definitely you have to care about the order. In particular, that would happen in this case, where I've cared about the ordering. Ordering matters, but you can still compute this object, and here's what it is. Okay. So yes, they're non-commutative, so it cares, and you should keep the orderings. Now, what is the okay? So yeah.
So in the bulk point limit, we would just replace these by actual momenta. Is that right?
Yes, that's right. That's right.
Thank you.
That's correct. Now, okay. So all this was double copy independent. This was, if you like, I think something I want to return to, just a way of thinking about amplitudes like objects in curved space-time. I want to return to it. That's been other things. It's not trivial. It'll work like very mechanically, but these are just objects that are like have Mandelstam, ST and U. They have ST and U. In endpoint, they have generalizations that look exactly like regular Mandelstams, except not commutative. So they're just interesting objects, I think. But if I return to the double copy story, we know what the mapping is, okay? And here's the mapping. Do everything we did before, okay? Except replace the color index with a killing vector isometry index, so capital A index. Okay, that's it. So we have instead of partial mu, instead of the generators of translations, I have the generators of the killing isometries. Okay, and here's the claim. Okay, we checked it, but you can see for yourself. You write phi cubed ADS correlators or phi cubed correlators in general symmetric spacetime this way, and you do this replacement, you correctly get the correlators in the chiral Lagrange in that theory at endpoint. Okay, how do we prove it? We use equations of motion, because the point is I can write equations of motion in curve space and do it this way. So it's a proven statement. All the stuff I said in flat space also applies for the phi cubed to pion mapping in general. The other cases, it's more confusing and I don't fully understand it, but in that case, we can see an endpoint, a version of this double copy. Okay, good. So again, I'm at like zero time, but let me really try to get to the last part, which is actually in some sense maybe the more interesting part, which is the double copy at all perturbative orders. Okay, so the last thing I'll talk about. And the idea here is the following. Everything I've said is at tree level, equations of motion, limited context, but general D, I think it's offered some insight. But we decided to jump. Yeah, sorry.
The fact that these don't commute, don't they introduce any ambiguities in this prescription?
Very good. It doesn't for phi cubed, because phi cubed doesn't have any derivatives to start with. So very good. Yes. In a theory with more derivatives, with you start with theory like 40 derivatives and try doing this, there's confusion in terms of ordering ambiguity. Like when you do the mapping and there's already derivatives, do I interlace them inside, outside, or what? But as I said, if you take phi cubed, which starts bleached, purely clean, it's unambiguous. It's actually precisely these ordering ambiguities that make the higher order cases confusing, but not obviously, we didn't push it further, but it didn't obviously not work. It just required exactly grappling with that. But for phi cubed, there's no issue because you don't start with any derivatives. So adding derivatives doesn't add ambiguities.
So in particular, Yang-Mills to gravity would be difficult in this.
Oh, for sure. And on top of that, like I haven't talked about spin and so on. I mean, obviously there's the natural way of thinking about it in terms of if we did ADS, like an embedding space and adding including spin. And some folks have thought about that actually. I personally haven't, but it's not like super trivial that it could be extended. I'll say personally, it takes work. I think some folks were claiming it can be done, but it's definitely not like just snap your fingers. Yeah.
Thank you.
Yeah. Good.
Also,
so
one more question. I mean, when you do this kind of thing in ADS, the natural question would be, what is happening on the CFT? CFT, it is a little bit of reminiscent, probably misguidedly, with the Sugawara construction. And is there any relation to that or anything else?
Right. So yeah, the Sugawara construction I think is coupled to the double copy, but not through these means. So I think actually if you look at the I'm sure they mentioned this. This is probably an obvious thing to them, but in celestial holography, the soft theorems in gauge theory and gravity are dual to the ward identities of the CFT. So like insertions of a soft graviton or dual in the 2D CFT to insertion of the stress tensor in the CFT. And if you had gauge bosons, they're spin one currents. And there is a Sugawara construction, which would tell you that like merging two gluons should look like a graviton. Okay. And I think in that case, for like the soft emissions, like that's kind of exactly what's happening. It also relates to the fact that in certain collinear limits of gluons, you can get like a graviton amplitude. So I think it's connected in that way. Here, I haven't thought about it. I mean, Sugawara is, I think, a 2D story, but and for a general CFT, I don't know. I haven't tried making a connection like that here. It would be super cool to ask, though. I mean, I see what you're saying. You're saying this is a statement about a Witten diagram, boundary correlator. Might as well just be the CFT correlation function. What is this operation? And I don't think anyone's looked at that, actually, kind of ironically. I mean, at the CFT, people have studied it in the bulk gravity calculation or the bulk ADS calculation, but kind of grappling with what this could mean very explicitly in the CFT. I mean, at least it might be about ignorance, but I don't know if anyone studied that super explicitly.
Okay, thank you.
Yeah, very good. Good. So any questions? Let me move on to the last part of my talk, which is double copy at all non-perturbative orders. So, okay, so everything I've told you was general D, but sadly tree level. So once we understood these things, like we immediately had a goal, which was like, let's find the simplest version of the double copy, the lowest dimension, like and like basically the easiest version of the double copy, and ask, can we make it non-perturbative? Can we make it all loop order? Can we make it true for large field configurations? Like, what's the most we can do with the simplest theory of the double copies, essentially? Okay, and it turns out you can do a ton, and that's the last thing I want to talk about. Okay. Turns out that in 2D, okay, so I'm going to think about theories in two space-time dimensions. There is a nice a group theoretic fact that we'll use, which to my knowledge was originated by Jens Hopp a long time ago, which is the following. If you look at the Lie algebra for UN at large N for odd N, it's actually locally isomorphic to the actually, I should say volume preserving diffeomorphisms on the torus. Okay, so let me tell you what I mean by that, and then I'll explain the connection. Okay, so here's the point. Think about UN, just for finite n for the moment. We're going to label the generators of UN in the following way. Okay, so UN has n squared generators. We're going to label each t by some p, which is a vector of Zn cross Zn. Okay, so in other words, this is an n squared dimensional space, and p lives in it. So it's the two-dimensional Zn valued vector, or like spinner, if you like, two-component object. This is a way of labeling the objects. This is what Jens Hopp showed. And then, but you label them in this way, okay? And I'm calling the labels P. So Pi and Pj are like the two different choices of generators. And I'm calling them for a good reason, because they're, of course, going to end up looking like momenta in a second. But you can just compute what the structure constants are. Okay, if you do that, okay, this is what you get. You get sine of this angle bracket over n, where this angle bracket is just the only natural, if you like, Lorentz invariant in 2D. This is just what comes out of the calculation. Okay, maybe I should emphasize, I'm using spinor helicity, but I'm not using 4D. It's just the natural 2D invariant. And here I've taken a large capital N to get the structure constant, which is just the angle bracket ij. In terms of the bookkeeping, what's important is that momentum conservation, it kind of falls out of it, okay? It tells you that Pi, Pj, Pk only couple at a structure constant if momenta is conserved in the 2D space, this 2D space in Zn squared. Okay. Now I've taken n equals infinity. I should mention that, of course, if I keep n finite, this actually has a name. I'll get to that in a second. But for n is infinity, this is a very famous algebra, which is just the Poisson algebra. And this is the Poisson bracket, right? What is I and j? It's like the P0 and P1 components antisymmetrically combined. That's just ddt, ddx, okay? Literally Poisson bracket. Okay, so this is the Poisson algebra. Okay, so at large n, un for odd n becomes the Poisson algebra. If I take finite n, it's actually the Moyle deformation of the Poisson algebra, very famously, very nice like modification of quantum mechanics that has some cool properties. So it turns out you can actually keep n finite and it looks stringy in some explicit sense, which I won't elaborate on, but it's kind of a like higher dimension operator correction to the n equals infinity limit for what I'll tell you now, but you could do it, okay? But let me take n equals infinity here just at the start, or n large, okay? And now here's the mapping, okay? So the color algebra goes to the Poisson algebra, which is also isomorphic to the diff algebra, okay? Poisson and, yes.
Misunderstood, but does this mean that UN, the standard UN algebra, is this Moyle deformation of this thing?
Yes, you can think of UN. Yes, you can think of UN as the Moyle deformation of the Poisson algebra. Yes.
I see. So a different name for it, but probably
it's a different name for it.
It's a better basis for it and so on. I see.
Yeah, it's just another name for it. Finite n has a good, well-tread name elsewhere in HepTH. Yes, indeed.
And then, can I ask a tangential question? I mean, maybe at infinity you could talk about diffeomorphisms of S1 times S1 times S1, three things, let's say, and then one can do a Moyle deformation probably. And is this familiar from like a UN kind of thing?
Oh, sorry. Are you asking about the UN subgroups of SUN?
No, sorry, this was a very tangential question. Let's say you had S1 times S1 times S1, then the diffeomorphisms of that, 3 copies of S1, and then you do Moyer deformation of this. I don't know whether it's possible. It would be unique. Would this be some sort of an algebra?
So I wouldn't know offhand, but if you look in this Jen's Hop paper, they talk about other diff groups, not on the torus, but on, I think, spheres. And I think maybe for like even n, there's other choices you can make. And he talks about it. He even talks about some product groups. There's some broader set of tricks in play that I'm not using, but if you look at the paper, you might glean something from it. It's like totally forgotten by everyone, but in the end, it's just like a bunch of Lie algebraology, so it's easy to read. But I don't know offhanded, but we've asked this. Well, you'll see why we asked this, but I'm interested in diff not just in two dimensions, but 3 or 4. So we're asking this question. So it's not like it generalizes to any manifold, certainly, but for some groups, there's generalizations that he talks about. Is that cool? Yeah.
Great, thank you.
Okay. Good. So okay, but what's the upshot? The upshot is, well, color algebra still goes to diff algebra. It just turns out that in 2D, the diff algebra is the Poisson algebra. Okay. In other words, you can think of this epsilon mu d mu v as J nu. That's all it is. Okay. It's a way of writing J, which is automatically conserved, right? J mu was conserved. Here I'm writing it as epsilon of a dv, like it's just a d of something else. So it's d squared is 0. That's all. Okay. Now here's what's cool. In now 2D, this n goes to infinity limit is it's now a very mild change. Like take your gauge theory and just take the limit. And now we can apply it to the off-shell Lagrangians, correlators, and actually to integrability, which is the very last thing I'll say. Okay, here's the mapping. It's the same story as before, but in terms of like these V fields. So it's just the Poisson bracket version of this. Okay, but here's the Lagrangian. Okay, so here's the off-shell Lagrangian formulation of this double copy. I start with phi cubed. So this is not the equation of motion, it's the Lagrangian, but I'm starting with it instead. Okay, this is the Lagrangian. If you take do the mapping, which is essentially sending phi, a goes to mu and then this, but secretly it's just sending n to infinity. Like that's actually what it's doing, because it's turning the structure constants into the action of diffeomorphisms. You do that, and then you identify those d mu's with the space-time space-time derivatives. You get this mapping of actions. Okay, so the first thing is biojoint scalar theory. The second thing should be NLSM, and indeed it is. It classically is equivalent to it, but it actually its form that you get is actually has a name. It's called Zakharov-Mikhailov theory. It showed up in like the very first papers on integrability, some of the very first papers on integrability, and it's a 2D theory which is classically equivalent to the NLSM in 2D, or the principal chiral model. So it's classically equivalent to the PCM.
Sorry,
do it again.
You said this and I missed. So when you think of this n going to infinity limit, it's like the new direction is kind of, I don't know, it feels like it is coming out of this internal direction, right?
Yes. So in principle, it's just some abstract internal index, and it's just some in z n as n goes to infinity. But the key is like you're taking n goes to infinity and then doing a non-trivial operation, which is identifying that space-time, that 2D space-time, with the original space-time that the fields live on. Right. Yeah. So this FA bar, B bar, C bar is n goes to infinity. It looks like differential operators and angle brackets like angle ij. And then the move is to think of those angle ij's as literally acting on the 2D momentum. And that's the map. Yeah.
But could you also have just thought of it as generating a new space? So now the 2D theory became a 4D theory?
Yes, that is another way of thinking about it, which would be possibly the way we should think about double copy. Like, so I'm saying it's not clear whether double copy is secretly a whole second copied space where we're looking at very specific, like entangled motions in that space, that you could think of it that way. And you're afforded that luxury to do. But for the moment, I'm just keeping them in the same space to keep it clean. But definitely, the second thing would be similar to what people do in double field theory, where there's like an SOD comma D, like literally, like actually another space in double field theory. But that's not what I'm doing here. just because I don't plan on taking anything different in that vector space anyway. But you could, and maybe that would be fruitful to study. Okay, good. Now the point is we get action levels double copies. This is the Zakharov-Mikhailov theory. It's just a phi cube theory, but with more derivatives, with 2 derivatives. And I should say, crucially, it's classically integrable. Okay, so like the PCM, it's integrable. And this one is classically equivalent to PCM, and it's at least classically integrable. If you do it one more time, you get the special Galilean action. So literally the Galilean action in the original Galilean papers is this in 2 dimensions. And this theory isn't just integrable, it's free. Okay, so this special Galilean theory is equivalent up to a field redefinition to a free theory. Okay, so the kind of order operations here is we start with phi cubed, which is like interacting. We get to an integrable theory through the double copy. So it's not quite trivial, right? It's S matrices above 4-point are trivial because they factorize into 4-point, but there's still some 4-point because they're integrable. And then the Galilean is like trivial, totally trivial. Okay, so like there's an integrability that's being inherited here, which I want to tell you about. But the kind of key point is special Galilean is like 0. Okay.
Sorry.
Now, yes.
In this version of the double copy, you're not really replacing the color index with a kinematic index, right? You're literally on the phi field, you're sort of getting rid of the color index, and in the FABC, you're doing this.
That's right. The reason you can do that here is that if you like the this VA is going to epsilon d mu v. So like the free vector index has become a derivative. That's a nice feature in 2D because I can use the Poisson algebra. Yeah. So if you like, if I thought of this whole thing as J nu, then I would have like a free mu index. But the point is like that d mu is doing that job. So indeed, it actually kind of simplifies the diff, which is that B isn't going to Lorentz index, it's going to the derivative of the mu. Indeed.
Right. Right.
Yeah, it's just
but if you did your thing earlier where instead of writing instead of starting off with the phi, but having your currents instead, and try to do the same, the second line of the substitution at the level of currents, then what would you get? Would you get something else?
Here's the thing. So you do at the level of the equation of motion, you just get what I got last time.
No, but this is now a different replacement, right? It's not the same as last time. You now, when you do this replacement
so
of
if you use the equation of motion and then you plug this in, you get the equation of motion of this theory. Yeah.
Oh, you do. Okay. Cool. Cool.
Yeah,
cool.
Yeah,
okay. Okay. Thanks.
Okay. Now, if you look at off-shell numerators, okay, you can see the structure constants are just epsilon. Like the structure constants are just angle brackets. Okay. Which means a product of 2 structure constants, a product of 2 vertices is a product of angle brackets. So this is just like spinor helicity angle brackets. NS, NT, and NU are these objects, which are like spinors, like literal products of spinors. And they sum to 0 by Schouten. Okay, the Schouten identity is the kinematic Jacobi identity. And it's now super duper off shell, okay, at least in the perturbative theory, if I computed loops in this theory, okay, at every order, I drew like a 17 loop diagram. The structure constants just manifest this. Okay, so this would be in all orders in perturbation theory, double copy is manifested. So every loop integrand you write in this theory would automatically have color kinematics. Okay, now we can also apply double copy to currents. I did that like 30 minutes ago. But what's cool is we have a lot more currents in this theory. Okay, so of course, famously, you can build a whole tower of conserved currents in the principal chiral model. You can also do it in this ZM theory. You can build this lax connection and a Wilson line from it. It depends on some free parameter lambda. And famously, if you just series expand in lambda, you get an infinite tower of conserved currents. Okay, that's why this theory is integrable. Now, this all here is in terms of the original principal chiral model type theory, the pion theory. So there's A's. But you can now do the replacement. Okay, just replace A with d mu, and you get, if you like, a Wilson line built from diffs. You get an infinite tower of conserved currents that you can check is still conserved. Okay, so this proves that the special Galilean theory is also integrable, which is expected because it's free. Okay, so the double copy just works here, and you can see all these properties mapped nicely. The Wilson line included. Okay, this is now the last thing I'll mention, which is, everything I've said here, it's at action level, okay? So I can do something pretty amusing, I think, which is the simplest version of double copying numerical relativity. Okay, so what do I mean by that? So numerical relativity is still classical GR. Okay, it's not quantum gravity, it's classical GR, but it's strong field. It's like, G is finite, the field excursions are big, so it's classical, but very hard to get to in tree amplitudes. It's there somewhere, but very hard. Okay, let's do the double copy in 2D for strong field non-perturbative classical solutions. So here's what we do. If you like, it's a check of everything I've just told you. What we're going to do is, this is the first and only numerical double copy that's ever been made. And here's how we do it, okay? We're in 2D. So in 2D, I can like solve numerically with like nsolve on a computer. I can find classical solutions to equations of motion, okay? So what I do is I take the special Galilean theory and I just take two blobs and I scatter them. Okay, like literally scalar field blobs in 2 dimensions, scatter them. There's one space dimension, one time dimension. I can just solve for its evolution. Now it's a special Galilean, so it's secretly a free theory. Okay, so what happens? You see these two blobs hit each other, they go crazy, okay? But they always pass through each other because there's a field basis where they're free, okay, where they just don't see each other at all. Of course, that's not the basis we're in. We're in a basis where it looks complicated, but they do a lot of crazy stuff before they scatter. Okay, so you just solve for that solution and just check that they pass like ships through the night in this theory. That's this top solution. This 5x we just solve for numerically, and then we extract its Fourier transform phi tilde. Yeah, that's just me solving. Now, if the double copy is correct, then here's what it means. It means I should be able to build a pion or principal chiral model solution from the Galilean solution. Why? Well, the Galilean solution is just a pion solution where n went to infinity, where the number of colors went to infinity. So what I can do is take that phi tilde of p, like it's just a function of p, and then I build a new matrix function where I take phi tilde p and I address it with TP, which is that generator, that like literal n by n matrix of SUN labeled by p. Okay, so this is me building like the pion object, which at infinite n equals a special Galilean solution. Okay, but it's instead just a big matrix. Okay, so I've built a big matrix function. Now, I can check now whether that function satisfies the equations of motion for pions. That's the check. I built the solution in one theory. I built the double copy from it, or really maybe took its square root, if you like, from it. And then I'm going to check that this is a solution. So if it gives me garbage, then this failed. If it is a solution, then I've built a new solution. And this new solution is interesting because pions should scatter. Pions hit each other. But this solution should be somehow bleached of that information and should look like two free particles, despite the fact that it has interaction. Okay. And the next slide is just the check of that. So the next slide is a picture of this matrix, like sliced in some color direction, the matrix phi. And I'm going to show you how we can check that it is indeed a correct solution. So what we literally did was build this function for n is like 201. Some large odd number, like literally built a giant matrix n by n and just check that it satisfies the equation of motion. And here's what you see. Okay, so this looks like a biology talk. This is like a second last slide, so bear with me. But here's a picture of the scattering. The x-axis is the horizontal axis is position. The up-down axis is time. So what you're looking is two particles scattering. Okay, so I'm initializing plus and minus is like value of the field. So it's like a plus field and a minus field. And they're coming in and they're hitting each other and they pass through each other. Okay, so this first panel is just the value of the field phi in some color direction. Okay, some color direction we pick. Phi tt is its double time derivative. Phi xx is its double x derivative. And these bottom panels are terms in equations of motion. Okay, the purpose of these bottom panels is just to convey to you that every term in the equation of motion, namely the kinetic terms and the interaction terms, are non-trivial. Like they're not like zero trivially. I'm not like adding zeros. They're like interacting, they go crazy. But when you add all of them up to get the equation of motion, you get a residual, which is essentially 0 up to 1 over, that's the 1 over n, capital N. Okay, so this last panel is checking that the equation of motion is satisfied throughout the evolution after I construct, using the double copy, a new solution to pions. So this residual is a kind of victory. It's not exactly 0 because I can't take n to infinity, but I can take a big matrix. You can also just look at the actual process. So this is the two things scattering. These are their various time derivatives and their interactions. Here you can see these two panels, they wobble a great amount, but they cancel, okay, not 100%, but they cancel to a large degree because we can't take the matrices infinitely large. And this is essentially, like if I had to draw an analogy with what this would mean in gauge theory, it would be like me simulating something in numerical relativity, extracting a gauge theory configuration that corresponds to that GR solution, and then checking that it satisfies the Yang-Mills equations of motion. That's what this is, except in 2D, and it verifies that the story, what we're telling, actually makes sense. Okay, good. I'm sorry I went a little bit late, but let me just state my conclusions. So scattering amplitudes have lots of cool things they can teach us about amplitudes. I only mentioned the double copy, which connects gravitons, gluons, pions, and other things, but there's way more stuff. Other things I'm actually thinking about now, which I could tell you about string amplitudes and so on, but let me not do that. But this is just one brief snapshot of it. There is, I think, a very crisp field theory explanation for the pion double copies. Double copies involving pions just have this operation and its color goes to diff. It's definitely exotic. It's not like a minor modification, but it's something which you could see if you write your dynamics in the right way, and you can double copy currents and kind of just features of your theory mechanically and maybe learn something. And I've applied this now. We've applied this to the equations of motion, but also curve spacetime, and in the case of low dimensions, full-on Lagrangians in all loop order and non-perturbative numerical solutions. And hopefully we'll be able to tell you more in some point in the near future. Okay, that's all I want to say, and thank you for your attention. Let me stop there. Thanks.
Thank you so much, Cliff, for a wonderful talk. Any questions?
Maybe I can ask the following. In the last part of your talk, you explained how this large N gauge group sort of grows to extra dimensions. And then you sort of insisted on identifying this extra dimension, these two extra dimensions with the actual spacetime dimensions. Mm-hmm. But if we would just take a path integral of that theory, of the theory with the color, then isn't it the case that you are explaining to us that we started with a two-dimensional theory and color, then that path integral is the same as a path integral in a four-dimensional theory?
Very good. Yes, that's correct. And, yes.
Sorry, and what the sense I got was that then you were making some sort of consistent truncation of this theory by, right. There's a Z2 symmetry which flips the two R2s, and you impose that Z2 symmetry to say that what's happening in this R2 is the same as what's happening in that R2, and that's something you can do classically, but presumably you cannot do that quantum again. Is that
excellent? Very good. Absolutely. So indeed, I started with just the physical two. There was, strictly speaking, an internal extra two. And if I just kept that theory, the color sums would be like an extra dimensional sum, never a sum within the space we're talking about, indeed. And precisely, it's only if you identify them that something happens. That actually, to me, explains why the double copy procedure is a loop integrand statement. Okay, it's a statement before integration, not after integration. This, I think, explains why that's true, because the integrands are just like diagrams you string together. It has this property. But if you literally do the integrals, okay, the theories now become different, which of course had to be true because Yang-Mills is renormalizable, gravity is ultraviolet divert. I mean, the integrated expressions could not be the same. And I think that is precisely why I don't think at some deep intrinsic level, it should work quantum, like post-integration. I don't think there's a quantum version of this. I think it's a statement about classical trees, which is why you could still apply it all orders in perturbation theory to the extent to which you're building them from trees effectively. So indeed, that's actually why I think, I mean, that's my pessimism for this. Maybe I'm hopefully wrong about it, but that's why I think it won't be a quantum statement. It will just be a classical statement, or at least a statement in all orders in perturbation theory at perturbative loop order at integrand level, which is also precisely the context in which it's been used, applied, and studied in amplitudes, never in the integrated expressions. Yeah.
Thank you. But maybe it could be quantum statement in two higher dimensions.
Sorry, can you say that again?
Maybe it could be a quantum statement in two higher dimensions in a different theory.
That's true. Yeah, absolutely. That for sure is possible, and it could be. I think it probably is a quantum statement for enough supersymmetry and so on. But I guess as just a kind of field theory minimal unit, I don't believe I should expect more. But for higher dimensional or more symmetrical cases, I think it could certainly be true. Yeah.
Any more questions? If not, let's thank Cliff for a wonderful talk again.
Cool. Thank you.
Thank you so much, Cliff. This is by far the most understandable talk on the subject I've ever heard. I mean, by an order of magnitude. Thank you so much.
My pleasure. Yeah, they may be a comment on understandability of the talks, but I try. It's very technical. But I think if there was an upshot to my whole talk, it's that we don't have to just be buried in the higher loop diagram. There is actually cool field theory, I think, living inside some of these structures. This one of many, which is like open. It's like open season on those things. if you're just
Very
willing
nice.
to just think about them, you can maybe learn something. So if anything, the one thing I learned here is that pions are phi cube theory, but where one of the flavors is diff. I don't know. That's a new fact for me. Yeah. Anyway, thank you for having me. Yeah.
Bye.
All right. See ya.